a solid. I think that's a solid. All right, so then there's different types of reactions. Synthesis is one product from a multitude of atoms or chemicals or elements or whatever. And that would be, for example, if you have a bunch of baking things and you mix them all together and you make one cake. There was a bunch of stuff and then you made one cake. So the cake weighs more than any one of the things, the flour, the sugar, the eggs. But actually, if you weighed up all that stuff and you weighed the cake, it should weigh the same when you're done, right? Hopefully. So synthesis, if you know what synthesis means, it means making one thing from a lot of things. Conveniently enough. All right. Classifying, we have decomposition, one reactant. So you have one thing breaking down into many things. And here's a log. And we talked about dead squirrels, that when a squirrel gets hit by a car, it starts to weigh less and less as more and more things from the squirrel go away, from ants or birds or fungus or whatever it is that's going to eat the squirrel. So when you have one thing and it's going into multiple things, that is decomposition. And then single replacement is when one usually element breaks up a compound so that the one element is now part of the compound and one of the elements in the compound is left out on their own. For example, here done by Mr. Philip Redkin, iron comes in and knocks copper off the sulfate, and then copper's by itself and iron has a sulfate. So here's the iron, it takes the sulfate away, and now copper's all by itself. All right, and then there's double displacement or double replacement. I keep saying the same, I keep mixing those up, but just know that I can say either one. Here's Daisy and Peach, or Peach and Daisy. Peach and Daisy, I think. All right. Mario and Luigi, and then Mario was with Luigi, now he's with Peach. Luigi was with Mario, now he's with Daisy. So that's double displacement. So they come in pairs and they leave in pairs, but they're not the same. So here you can see calcium leaving with nitrate, it came in with bromine, and silver leaving with bromine, it came in with nitrate. All right, and here's a nice thing here where the silver is taking the chloride from the potassium, and the potassium is taking the nitrate from the silver. Look at that. Thanks, Philip. All right, last one is combustion. In a combustion reaction, you make carbon dioxide and water from some hydrocarbon and oxygen, and this is how we burn things and get our fuel and whatnot. And that's that. Pretty much diatomic molecules. Remember, there are 7 that exist as diatomic molecules. I've had more driving forces. We don't need to talk about that. All right, exothermic and endothermic. This we did talk about. So reactions involve energy, and you need to either have energy released or absorbed. If it's released, we say it's exothermic. Exo meaning sort of leaving, and endo going into means it absorbed. So most chemical reactions are going to need a little push to get them going anyway, and we call that the activation energy. So even if something like burning of carbon. Anyway, like the magnesium we did, or if you burn a piece of paper, right, you still need, or if you light a fuse, right, you still need to get things moving in a certain direction. So exothermic reactions, you'll have something like H2 and O2, which when you light them on fire, make this huge sonic boom. It's really cool. And they do that because they're forming water, which is a more stable product. And as these form that, they, even though you need a little activation energy, they're going downhill, they're decreasing in energy. So that's exothermic. Energy is being released from these to get down there. And the reactants are of higher energy. And the products, energy is like a product, right? So you get the water plus all this energy when an exothermic reaction happens. Now, the opposite of that is an endothermic reaction. I did this. I took water and I hooked it up to a battery to make it H2 and O2. So for water to get all the way up to H2 and O2, you got to put energy in. So water is of lower energy than the H2O2. So to get up the hill, you got to put some energy in. And then you're going to have a large activation energy in this case. It takes a lot of energy to get up here. Products are generally higher than the reactants, and energy is like a reactant. You have to add energy to this to get up to that hill. All right. Talked a little bit about entropy. I didn't cover this in this test. It'll come back though, but entropy basically means it takes energy to make something ordered. And we talked a little bit about this, that the elements up here And we did this with the switcheroos where we put copper. Where's copper? Copper. Here it is. In with silver. So silver was in a silver nitrate, and we put a piece of copper in there, and the copper went into the solution, and the silver came out of the solution because silver is more stable than copper. Basically, copper would prefer to be in solution in the presence of silver. So we got a bunch of silver crystallizing on the copper wire, and then we saw the copper go into the solution and turn it a little bit blue. And then we did the zinc in acid, and we did the copper in acid. Nothing happened when copper didn't make H2, but zinc did make H2 when it was thrown in acid. And then we talked about what would happen, and some of you did it with magnesium if you put it in acid. So you just need to realize these like to keep their electrons, stay as metals. They have high electronegativities for metals, and they're pretty stable as is, and that's why we make jewelry with this stuff. And that these things are not stable, that you just throw these in water and they start a fire. So they will lose their electrons in a heartbeat to become ions, and they have very low electronegativities because of that. All right, we didn't really do that. We talked about that already. And like aluminum foil, if you ever noticed when you cook something acidic with aluminum foil, it'll all get kind of sticky and nasty because the acid is reacting with the aluminum. And that's a thing. All right, so we didn't really do much of this. Let's go back to dissolving. So we did do with double displacement. If you put a bunch of ions into water and some of them decide to get together and form a solid, we say that's a reaction. And the alternative to that is you put a bunch of things into water and then they just stay swimming in water. Nothing forms together to make a solid. So then we say there's no reaction. And we did some of this with the precipitates. Now, I had originally thought this was a good chart, but it's not. I gave you a better chart. But basically, when you switch your partners, when calcium gets with sulfate and ammonium here gets with nitrate, you can look here. No nitrates are exceptions to being soluble. So that means anytime you see a nitrate, it's soluble. And sulfates are also soluble except for strontium, barium, mercury, and lead. So in this case, that would be calcium sulfate. So that would be no reaction of reading this. But you just know how to read the other thing that will be given to you, the crisscross one. All right, so that's some more. Wow, that's it. So that's all we did, I guess. All right, so is there anything else I wanted to tell you? Let me just show you real quick two things. Since I have your ear, you can stop listening now if you want to. But if you go to association of salt. All right, let me turn that off. So remember, as Simba said, or Mufasa. All right, salt has these pluses and chlorine minuses. So the pluses are sodium, and that water will go and pull those apart. So if the salt wants to stay together more than the water wants to pull it apart, then that's a reaction. So here you can see the positive hydrogens pulling away the negative chlorines. This is a better one. I should have shown this one. I just found this recently. And here you see the negative oxygens of water pulling away the positive sodiums. And if these things want to stay apart in water more than they want to come together, they dissolve in their aqueous. And if they want to come together, then we say there's a reaction. And there's certain things that like to stay together more than they like to be pulled apart. And that was good. And then the other thing I wanted to show you real quick is the H2 hydrogen reaction bubbles. Let's try that. Where's that lady? There she is. All right, so this is fun. This happened where the guy was talking to this woman about doing things, but basically, here's the fun part. All right.
We're going to see what happens if we add a little energy to that from the flame of a match. Okay. While they're in the palm of your hands. Alrighty. So what I want you to do here in just a second is scoop up as many of those bubbles as you can. Just skim them off the top. I'm getting nervous. Leave the water.
So these bubbles have hydrogen oxygen in them. Okay. And just to show you how good this reaction is.
And for everybody else in the studio, you might want to plug your ears because in 3, 2, 1. You okay? Yeah. You had a lot of bubbles there. That was and you know, cool thing about that, you're okay, right? Show your hands. Okay, I'm alive. Okay, dry your hands off. The cool thing about that is that reaction happens so quickly, it actually creates a supersonic shockwave. Yeah. I felt it.
All right, so
I can feel it. Yeah, I think you blew me away. Okay.
let's watch that in slow-mo.
Today from noon. Good, Carl. Thanks so much. I'll send it over to the guys. Sam Check Sports.
All right, slow-mo, instant replay.
2, 1.
All right, I forgot to show you that, but that is what happens when you have hydrogen and oxygen in water. All right, so hopefully that's something to help you study tonight. Oh, that's not what I meant to do. Here we go. Now.